This is Professor Tom Webster. I'm the editor-in-chief of the International Journal of Nanomedicine, and I helped start the journal back in 2005. I'm happy to be with you today to talk about why nanomedicine works. To date, there have been numerous reports in the literature, and it is well known that nanomaterials can increase tissue growth. From bone to cartilage to cardiovascular tissue, it is now well established that these small materials have unique properties to control and enhance cell functions. More recent studies are demonstrating that nanomaterials can decrease infection without using antibiotics. Moreover, they can limit inflammation and treat cancer without using pharmaceutical drugs. So this presentation will discuss some of the more fundamental science reasons why nanomedicine works. But let me start with a definition of nanotechnology and nanomedicine. Nanotechnology really involves the use of small materials to possess unique properties not found in bulk or larger materials. So when reducing the size of a material to the nanoscale, the definition of nanotechnology is that something unique will appear. Now, of course, we know nanoparticles can last longer in the body by avoiding immune system clearance. They can also penetrate certain regions of cells, whether they're bacteria or mammalian cells, to control responses. They can also dictate structure of viruses after attaching to render those viruses useless. These are all examples of nanotechnology applied to nanomedicine, which is the focus of our journal, International Journal of Nanomedicine. Now, when looking more closely at the fundamental question, why use nanotechnology in medicine, we can come up with two main reasons. One reason is simply that nanotechnology or nanomaterials mimic the natural structure of our tissues. Our tissues in the body are composed of proteins that are nanostructured. So cells reside and make nanomaterials. While that may sound like a worthwhile reason to use nanotechnology in medicine, it is fairly simplistic. And as we know, mimicking nature has not always given us the best solutions. For example, when you fly in an airplane, you don't fly in something that looks like a bird. So in certain cases, the argument of mimicking nature works, and in certain cases, it does not. So I would like to give you a more scientific second reason to look at nanotechnology in medicine, and it has to do with a fundamental property that changes in nanomaterials compared to conventionally used larger materials: surface area. Pictured on this slide is a medical device that is used today, which does not encompass nanomaterials, and a picture of a nanostructured implant material. As you can clearly see, the nanostructured implant material has significantly more surface area compared to what we implant today. That increase in surface area changes everything, changes properties, and it changes the way that cells will behave on those surfaces. And we explored that a little bit further and have actually created the first equation that can predict what size of nanoscale features you should put on an implant to promote its efficacy, whether that means to increase tissue growth, decrease infection, or decrease inflammation. We have an equation that can tell you, based on that chemistry you're implanting, what size surface feature you should put on that implant. That equation all starts with the fundamental understanding that protein adsorption is related to surface energy of your material. If you have a more hydrophilic surface, you will get more hydrophilic proteins to adsorb. If you have a hydrophobic surface, you will get more hydrophobic proteins to adsorb. So nanotechnology, by increasing surface area exposure of your material, can change the energy of that surface to in turn change cellular behavior. So the equation starts with this understanding of protein adsorption to surfaces. We then can ask ourselves the question, well, what contributes to surface area of a medical device? In our equation, we assume that surface energy of your medical device comes from two things: the chemistry you choose to implant, and we call this the chemical or ground surface energy, and the other factor is surface area of the chemistry you're choosing to implant. So we can come up with an equation where overall surface energy, E sub S, is related to the chemical ground surface energy plus the roughness of your surface. So what we can do in nanotechnology, nanomedicine, is manipulate the effective roughness of your surface. Shown on this slide is one equation that can describe effective roughness of your surface, and it's written in the Z direction, the height of your nanoscale feature. I could have also written this equation with X, length of your nanoscale feature, and Y, width of your nanoscale feature. But if you know what protein you want to absorb to your surface because it will promote bone cell attachment, you can then back calculate using this equation what your Z height, X width, and Y length surface feature should be. So as a demonstration of this, and there are many in the literature of using this equation to estimate surface features to promote the absorption of proteins that will enhance the effectiveness of your implant, can be seen on this slide. This is where we took polycarbonate urethane, a very popular medical device, put nanoscale features on that implant by using carbon nanotubes. We added more and more carbon nanotubes when going from A to D, which clearly increased nanoscale surface roughness. We did not change the chemistry, only nanoscale roughness. That in turn enhanced wettability of the sample. You can see when increasing carbon nanotubes in polycarbonate urethane, the water drop is more spread, and that results in increased hydrophilicity, increased surface energy. That in turn promoted the absorption of a protein called fibronectin, which is shown in G. Increased nanoscale features led to increased wettability, led to increased absorption of a wettable protein, hydrophilic protein called fibronectin. That in turn increased bone growth and decreased infection in our studies. Again, all of this accomplished without using drugs and simply modifying the surface features of your implant. Another example shown on this slide is how protein bioactivity can be changed using nanoscale features. As I mentioned, proteins are nano-dimensional. So by using nanoscale features, in this slide it's with polylactic glycolic acid, going from the left to the right, you can see micron to submicron to nanoscale features. We were able to get more proteins absorbed, and the proteins became more elongated after absorbing onto the nanoscale features. This promoted bioactivity. Nanotechnology can both increase absorption of select proteins based on surface energy, and then after absorption can control bioactivity since they are of the same size scale as the proteins themselves. So I hope in this brief video I gave you an idea of why nanomaterials and nanomedicine controls cell function. It's more than just mimicking nature. It's the unique surface energy that these materials can provide in the body to control initial absorption, which will control cellular behavior. Thank you, and if you want more information, I encourage you to go to our website, listed here, www.websternano.org. Thank you.